This is what the world, as we reconstruct it, looked like. This is a time when much of North America was covered with water, but in this area rimming our little basin, we had shallow enough water and our continent was oriented close to the equator. We developed massive reef systems, which essentially sequestered or prevented easy access of flow in and out of our basin. Now, if you take a bowl of water and you just keep a little water coming into it all the time, seawater, but keep evaporating, what do we eventually form? We form salt deposits. And so when we were talking about the major salt deposits that are mineable, these are in fact of Silurian aged. Again, these have been mined both by solution as well as by underground mining. I think I was asked to do some work for actually the legislature, because some people wanted to put some hazardous waste in something called the diamond crystal mines around Detroit. And they were full of water, and they said it's from diesel fumes of the equipment. But in fact, chemically, we could determine that it was groundwater, which meant that they had breached into this salt layer, which meant it wasn't a good place to put some hazardous substances. But that was a few years ago. In fact, this process of evaporation produces, this is a core that we pulled out of our core lab of some of these salts. And as we all know, Dow Chemical has taken advantage of these salt levels or of beds, in effect, instead of by mining at the surface, by essentially dissolving that material in the subsurface, bringing that brine up. And if you think about what evaporation does, it takes rare elements and it concentrates them progressively, such that what they happen to be is a place called Midland. I wonder why we call it Midland. It's sort of right in the middle of the basin. In fact, the final little bits of salt, or of water that are left behind after the salt, the normal rock salt is formed, is rich in such things as bromine as well as rare earths, and very mineable. And so Dow actually made their initial sort of step into the sort of the chemical world through that exploration and continue today. Sedimentary rocks are the reservoir within which all of our oil is found. And it's because it's the process of life at the surface which produces the organic material, which then is sequestered naturally within that sediment and ultimately then transforms into a usable hydrocarbon for us. And so when we began to look on a North American scale, we see that many of these basins that I pointed out earlier are in fact areas of major hydrocarbon production in the past and also today. Michigan is comparatively small compared to such things as the Gulf Coast. Here the depths of the basin exceed 25,000, 30,000 feet. Again, we have maybe 16,000 feet maximum. But we need to think in terms of where we're producing in here, and it turns out there are a few layers. Well, many of these stratigraphic levels actually have hydrocarbon potential. What's necessary for us to have geologically in order to make oil? First of all, we have to have a source bed. In other words, we have to have layers which have sequestered enough organic material through photosynthesis, so forth, and then brought to a deep enough burial depth to bring it up to temperature. Essentially what we have to do is distill off these hydrocarbons. And so we can talk about sort of an oil window in terms of temperatures. And we need temperatures somewhere on the order of about 90 degrees centigrade. That's pretty warm, right? That's getting close to boiling. Do you think it gets hot if you drill a hole here in the middle of Michigan? I'm going to get his name, Timothy. If I drill a hole in the ground here, does it get warm?
Not at first.
Yeah, it turns out a lot of groundwater in there. It's seasonally modulated. But as we continue to go deeper and deeper, usually about for every kilometer, every 1,000 meters, in this part of the world, the temperature increases about 30 degrees centigrade. So roughly right now at the base of the basin, if it's a normal sort of temperature increase, we'd expect it to be in excess of 150 degrees C. Do you actually know how hot it is in the bottom of the basin? Yeah, but and we know that earlier it was even hotter, which means that a lot of the Michigan basin has gone through this interval that's necessary for oil generation. And when it's buried a little deeper, it gets hotter, it actually produces natural gas. And so this represents, in part, the resource that we're mining today. I'm going to move into some work that I would say production strategies that have really been developing and expanding, certainly over about the last 10 to 15 years. And this isn't as clear as you might like it, but most wells, when I was working with Texaco years ago, we think of vertical wells. We drill down, get into a reservoir, and a reservoir is basically like an aquifer. It's a rock that has enough holes in it so the oil or gas can move between those holes, something we call permeability. And so that oil and gas could then migrate to a central pickup point, be pulled out, and then you would become, like the millionaires in Texas. We have removed a lot of the oil from those easily findable reservoirs. And now we start talking about unconventional plays or unconventional sources. And one of them is shales. I mentioned earlier that we have shale layers that in fact can serve as the source of that oil because they have a lot of organic material. But the problem is a shale is made up of very, very fine particles. If the way geologists tell the size of grains in the field is we take a little bit of it, stick it in our mouth and rub it between our teeth. And people think we're strange. We are. But the reason we do that is your teeth are very, very sensitive. And if it's clay, it's smoother than toothpaste. If it's a little bigger, you could do it. It's like that toothpaste they use at the dentist. If it's sandstone, it feels like your teeth are breaking. So with material that is that fine, with all of the water essentially taken out of it by compression, the holes which exist in that rock are not interconnected. It is a poor aquifer. It is called an aquitard. Essentially, gas or oil, which may be present in these layers, is trapped because they have very low permeability. It can't move back and forth. And so the question is, how does one produce a resource in something where the material you want to produce doesn't want to move or can't move? You do what's called hydrofracking and horizontal drilling. Instead of trying to simply frack or to break up the rock just in the vicinity of a single pipe, rather the new technologies now may put a vertical shaft down, drill stem down for several thousand feet, but then the lateral duration within that impermeable layer may extend as much as 5,000, 6,000 feet from a single well. And then they can radiate that in many directions, which gives you an area of potential production in a material that prior to that, oil and gas could not flow through. The process that creates that network of holes is this process called hydrofracking. And I'm sure that you folks have heard about this. I'll go through a couple of examples of it. Realize that in shale, if I want to break it up, if I take very, very high pressure water and basically push it into this formation, I expand it. And as I expand it, just as I was stretching continents and creating space, in the same way we stretch this shale, and as we do that, we begin to fracture it. That creates the holes, the fractures, the fracture network that then the gas can flow into. And depending upon the frequency or the density of fractures, it lets the oil and gas which is stuck within the shale, within the sediment, to actually diffuse into that water. Second thing, though, is that when they pump this water down, they run a lot of sand in it as well. Because as you begin to extract that water to take the gas out of it, the pressure comes off, the fractures come back together, and you would lose your porosity. So they use what's called a proppant. That's a good term. It props open the holes. And so they use a proppant and so forth. Now we're going to see later that they also use a lot of other things on this to try to enhance the production of hydrocarbons out of here, plus to also maintain the integrity of all of the drilling assemblies, essentially anti-corrosives and stuff of that sort. This, what we call unconventional play, which now is really moving more into what we call shale gas, is producing increasingly the bulk of natural gas in our country today. It really began in a large way with the Barnett Shale, which I can't see. Oh, here it is, right in here, in the Dallas-Fort Worth area. It actually turns out one of our alums was instrumental in discovering that field and its initial production. Subsequently, people have applied these technologies of hydrofracking, and these are all areas in which shale gas plays are being taken on. Note that the Antrim is one of these that has been targeted. This came out of there's an excellent, if you want additional information, I should have had the reference on here. Department of Energy put out a nice, concise, concise, 100-page sort of description of issues associated with shale gas in North America. And I can get that reference available for all of you. But in fact, as I began to explore this more, in fact, the Antrim is not as traditional of what I would call a true shale gas play, in contrast to a number of these in the Marcellus and the Utica, because it is already largely fractured. And so, as a result, we've been producing a lot of gas out of the Antrim for a long time. We may be able to get more. They suggest that there may be something like 2 million cubic feet of 2 trillion cubic feet of recoverable gas from the Antrim alone. And that's even though we probably have over 9,000 or more wells in it. But I'm going to point out that we're going to go into this in a little more detail. I'm going to point out there are actually other shales down deeper. And those other shales also have great potential. We don't need to go through all of these. It turns out that hydrofracking has been going on for a long time. So it's not a new technology. What's really new is the extent to which it's being used primarily in these shale fields. For a long time, people stayed away from these shales because production was just so low, except in things like the Antrim. Note that in the mid-30s, the Antrim shale was in fact really was a target of exploration. More recently, probably 10 years or so ago, one of my colleagues, Lynn Walter, worked with the American Gas Institute specifically on shallow Antrim gas fields, trying to understand why they were getting gas when they didn't expect it out of these. It turns out a lot of microbes actually can produce gas out of these rocks. So it's not just thermogenic, it's not just getting it up to temperature, but it's also a lot of microbial interaction that can produce it. Okay. These are some of the shale gas formations that are actively being explored today. Barnett Shale we know of. I put these, just highlight these to say that these are two that are active right now in Michigan. My impression was that most of the hydrofracking in the Antrim is just up in the northeast, right? Of the lower.
Michigan, across from Mann Street.
Yeah. But I didn't think there was that much hydrofracking going on. Most of it, they're using natural fracturing porosity in it.
They hydraulically fracture just about every Antrim well, but it's a small scale.
Okay, okay. But the Collingwood, I was aware of one test well, and now your state geologist said, in fact, I think you've got 3 test wells. And Collingwood is, in fact, I think, is probably going to be a pretty good producer, at least from the initial results I saw.
Jury's still out.
Yeah, one never knows. I shouldn't predict. I'm not a true oil geologist, so although I've worked with them a little bit, we call it's a greasy business, the grease business, and it's a good business to be in. A lot of my students work for oil. But I wanted to just sort of give you a sense where we are in terms of some of the major formations. This is the Antrim. It's largely a shale formation. Within, we're going to see actually buried at relatively shallow depths in the Michigan Basin, ranging from about 2,000 feet, actually exposed under glacial till in Paxton Quarry as you go up north. There's also the Collingwood, which, just to put it in perspective, remember this represents about 250 million years of sediment. What we were looking at in terms of the Antrim is right up here, and the Collingwood is much deeper. Costs are much more in producing these, and that may be part of the sort of the inhibition to produce it right now, particularly as we'll see the price of natural gas right now is very, very low. And so again, the commodity prices are